Hey guys, welcome back, and this week's video is going to be all about kinematics and how you apply calculus to kinematics. So first of all, kinematics is basically all about motion, so speed, distance, acceleration, and whatnot. And in this video, I'll be showing you how we can apply calculus to help us understand motion. So first, let's start off with the basics, and these are mainly the three aspects that are used in kinematics. So we have S of t, which is usually representative of displacement. And displacement is our change in distance from our starting position. So for example, this is my starting position and this is 5 meters, then my displacement is 5 meters. Or if this is my starting position and then I move over here, then my displacement is 10 meters. Or if I go here, again, it could be 5 meters. So it's just how far I am from my starting point, which is often the origin. And notice how all of these functions are with respect to time. And that's because when working with motion, we often use time as our independent variable in the sense that it's, for example, our displacement after 5 seconds, or our speed after 10 minutes, or our acceleration at the 5th minute, who knows. Then our second variable, or our second aspect, is velocity. And velocity is similar to speed, but it has a direction. So this is our change in displacement over time. And you can already start to think how this relates with calculus, like derivatives and integrals and whatnot. And the unit for displacement is often meters, and the unit for velocity is often meters per second. And lastly, we have A of t, which is our acceleration, which is our change in velocity over our change in time. And so the units for this are going to be meters per second squared. And if you're confused about the units, well, then just think that if this is our formula for velocity, then our displacement is measured in meters and our time is measured in seconds. So we're going to have meters per second. And if this is our change in velocity, then this will be meters per second, and again per second, which will be meters per second squared. So this is where the units come from. Now, let's start off with looking at our displacement. So say we're not moving, we're in the same displacement. This can be shown by, for example, if we're just constantly at the displacement of 5. If our displacement is constant, that means we're staying in the same position. What is our velocity, or what is our speed? Well, it's going to be 0. And if you look at this line, you can tell that its gradient is always 0. So S prime of t is equal to 0. And if you're making a connection in your head, you can see how this relates to our velocity also being to 0. Because our velocity is equal to our displacement over time, which is our slope, because our displacement, or our change in displacement, is our change in y, and our time is our change in x, and this is the derivative of S of t. Now, what if we are not stationary? Let's say we do have some movement, and let's say our movement is in a perfectly straight, uniform line. Then we can look at this, and let's say this is 1, and this is 1. So the slope of this is equal to 1, and this is the same thing as S prime of t is equal to 1. Well, then our velocity is also equal to 1, because each second we are increasing our displacement by 1 meter, meaning that our speed is a meter per second. And this is again reflected by the derivative, which is equal to our velocity. And let's look at one final example where we have some more complicated motion. Let's say this is our displacement. Well, then in order to find our speed at each displacement, we simply have to take our derivative of the displacement because, again, speed is change in displacement over change in time, which is equal to change in y over change in x, which is your slope, which is therefore your derivative of the position. So here, for example, this is my change in displacement, this is my change in time, and this is my slope, which is equal to the derivative. So if we summarize this together, we can say that the velocity is equal to the derivative of our displacement. Now let's move on to a graph of velocity. Well, let's say we have a constant velocity. What does that say about our acceleration? That means that our acceleration is equal to 0 because we're neither speeding up nor slowing down. And again, let's try to link this to our derivatives. Acceleration is equal to the change in velocity over the change in time. And in this case, this is going to be equal to our change in y over our change in x, aka our slope or our gradient, which is equal to the derivative of our velocity. Now, velocity is different to speed in the sense that it has a direction and not just the magnitude. So if we look at a different graph, for example here, then technically our maximum velocity is right here, but our maximum speed would be somewhere way down there because our maximum speed doesn't care whether we're going to the positive or negative direction. And so let's, for example, take a look at this line right here, and we can say that here, when v prime t is equal to 0, acceleration is equal to 0. And then you can see that as we're speeding up here, we then slow down here. And when we go into the negatives with our velocity, what that means is that we're changing directions. And this is because positive velocity means we're moving, for example, to the right, but negative velocity just means that we're moving to the left. So whenever you're asked about changes in direction and you're working with velocity, just look at where you are either in the positive or in the negative. And lastly, let's move on to acceleration. And as we've already said before, acceleration is equal to the derivative of velocity. But how can we relate this to displacement? Since the derivative of displacement is equal to velocity, and the derivative of velocity is equal to acceleration, then the second derivative of displacement is equal to acceleration. Again, I'm just taking the derivative of this, which is the derivative of this, so all I have to do is take the derivative of displacement twice. Now, let's go the other way around. And what I mean by that is, how do I get from acceleration to displacement, or from acceleration to velocity? And in order to do this, we have to basically just reverse our steps. And in order to go in this direction, so for example, from displacement to acceleration, we had to use derivatives. So in order to go back around, we have to use antiderivatives, which are aka integrals. And if you're not really familiar with this concept, then I really advise you to watch a video about it because it can really make or break your understanding. So let's say we have a constant acceleration. Then how do we find our velocity? Well, all we have to do is we have to reverse our steps. So in order to find our acceleration, we took the derivative of velocity. Now, in order to find velocity, we should integrate this back so we get v of t. In fact, we'll get v of t plus c, but don't worry about that because we're always going to have a constant that we can't really account for unless we're given data to work with. And this comes from the fact that if I integrate this, then the integral of the derivative is just the function itself. Again, these are fundamental theories of calculus that if you're not familiar with, again, just watch a video because it will really help your understanding. And this is how we go back to velocity. We integrate acceleration. And units really help with this because, again, acceleration is meters per second squared. And if you integrate that, you're basically getting rid of one of the seconds and you're going for meters per second, which is your velocity. Now let's look at how we can go back from velocity to our displacement. Let's say this is our velocity, then in order to get to velocity, we took the derivative of the displacement. And we can repeat the same logic that we applied to acceleration. And we simply integrate both sides to see that displacement, again, because the integral of a derivative is just the function itself, is equal to the integral of velocity with respect to t. Thus, if we want to go from velocity to displacement, you just integrate velocity. And again, if we're looking at the units here, velocity is meters per second. And when you integrate, you basically take away the second because you're integrating with respect to time. And you're just going to get meters, which is your displacement. So for example, here, if this is my point and my velocity here is at t equals 3, then the area under this curve right here is equal to s of 3 when we're looking at displacement from the origin. And now, if we sum this up together, then we're going to see that since the integral of v of t dt is equal to s of t, then the double integral of a of t dt is equal to s of t, and that's because the integral of a of t dt is equal v of t, and then we integrate that all twice to get s of t, which is our displacement. So let's sum of all of this up into a neat little note. And what this shows us is that in order to get velocity from our displacement, that is simply our displacement over time, which is our slope. Thus, we take the derivative of our displacement to get our velocity. Now, in order to get our acceleration, that is our change in velocity over time, so the slope of the graph of velocity, which is its derivative. So we differentiate the graph of velocity, which is the same thing as taking the second derivative of displacement, because again, our first derivative of displacement is velocity. Now, in order to go the other way around, we simply have to integrate because an integral is an antiderivative. So in order to go from acceleration to velocity, we integrate it. And in order to go from velocity to displacement, we integrate velocity, which is the same thing as taking the double integral of acceleration. And again, when you're doing this, don't forget the plus c. So for example, if I'm doing the integral of v of t dt, that's going to be equal to s of t plus c, because there's always this constant that we have to add when working with integrals. And just as a final note, here I think is a relatively neat diagram showing you these steps that I have just described and how in order to go into the right direction, you differentiate it, and in order to go back, you integrate. And this is all based on the principles of antiderivatives being integrals and on the fact that you are looking at the slope. So the slope of s of t is your v of t, and the slope of v of t is your a of t. So I hope you enjoyed. I hope you gained some understanding. And what really helps is simply practicing. So have fun and see you next time.